In the weird world of quantum physics, there are rules. At least, we thought there were. For some of the most powerful quantum effects to even exist, we've always assumed that electrons had to act like neat, well-defined particles. Picture them as tiny, predictable marbles zipping through a material. This particle picture is a cornerstone of modern physics, the kind of foundational stuff that wins Nobel Prizes. But what if the rule is just wrong? A team of physicists studying a strange metallic compound just found out it doesn't play by the rules. They cooled it down to temperatures colder than deep space, expecting its electrons to dissolve into a chaotic mess. Instead, right in the middle of that chaos, a powerful quantum effect appeared, one that our textbooks say should have been impossible. To get why this is such a big deal, we need to talk about topology. In math, topology is all about the properties of an object that don't change when you stretch or squish it. Think about a bread roll and an apple. You can smush one into the shape of the other, so topologically they're the same. A donut, though, is different. It has a hole, and you can't create or destroy that hole just by squishing. That hole makes it topologically distinct. Physicists pinched this idea for the quantum world. A material can have what are called topological states, which are incredibly stable electronic properties. Like the donut's hole, these properties are protected, meaning they can't be easily messed up by tiny flaws in the material. This makes them the holy grail for stuff like quantum computers and hypersensitive sensors. But for decades, every theory we had for these states started with the same assumption. You need well-behaved electrons that act like particles. Enter a funky compound made of cerium, ruthenium, and tin, or N6. A team at TU Wien, led by Professor Silke Buehler-Paschen, decided to see what this material would do at temperatures just a hair above absolute zero. At that extreme cold, the material does something bizarre. It enters a quantum critical state. In this state, the material gets stuck between two different electronic phases, fluctuating wildly, as if it cannot decide which one it wants to adopt. It's a mosh pit of pure quantum chaos. Here, our cozy idea of electrons as distinct little particles completely evaporates. They lose their individual identities and become a blurry, fluctuating sea. According to the rulebook, any hope of a stable topological effect should have died in that chaos. But a stubborn little theory predicted something else entirely. So, researcher Diana Kirschbaum put it to the test. She started looking for a telltale sign of topology, the Hall effect. This is when a voltage mysteriously appears sideways, perpendicular to the flow of an electric current. Normally, you need a powerful magnetic field to force this to happen. But in the quantum-critical chaos of N6, they found a clear Hall effect with no magnetic field at all. This spontaneous Hall effect was popping up all on its own, a direct result of the material's bizarre internal state. This was the smoking gun for topology. What they were seeing was a beautiful paradox. The charge carriers were creating a stable topological signal, as if they were well-behaved particles, even though the whole idea of a particle had already broken down. As Professor Buehler-Paschen put it, this was the key insight that allowed us to demonstrate beyond doubt that the prevailing view must be revised. The chaos wasn't the enemy of the quantum effect, it was the source of it. This discovery doesn't just bend the rules, it shatters them. It shows us that topological states are far more common than we ever imagined. They don't need a neat and tidy world of individual particles to show up. They can literally emerge from the complex, collective dance of a quantum critical state. The team, working with theorists at Rice University, gave this new phase of matter a name, an emergent topological semimetal. And here's the kicker. The experiments showed that this topological effect was strongest right where the quantum chaos was most intense. When the team applied pressure or magnetic fields to calm things down, the topological effect vanished. The rule wasn't just broken, it was flipped on its head. Chaos was actually a required ingredient. This is more than a head-scratcher for physicists. It's a new treasure map for discovering revolutionary materials. Instead of searching at random, scientists now know to look directly into the storm, at quantum-critical materials, which are much easier to spot. This could fast-track the hunt for new materials to build fault-tolerant quantum computers and ultra-precise sensors.